then she did his PhD at ICS. Then she has two postdocs here at IISc and also at HLI, and now she is a postdoc at KIPMU.
Thanks, Devalit. So before starting, I would like to thank Professor Bhattacharya for giving me visit, and special thanks to Ranjan for making a place for this talk within this busy schedule. So today I will be talking about light scalar long-lived particle searches at FCC-ee. My talk is based on this paper, and I will not discuss this paper fully. I will just discuss the scalar searches, and this paper is with the collaboration with Biplab, Camellia, Harbi, Shigeki, and Ritoja. So this is the outline of my talk. First, I will briefly talk about why LLP is needed. And then I will discuss about the ongoing and proposed LLP searches at the Hadron Colliders. And finally, I will discuss LLP at FCC-ee that we have considered in this paper. So we all know it has been a decade past the Higgs discovery, and we are yet to get any positive significant new physics particle at the collider. And it's a high time to rethink our assumptions behind these searches, and we should give attention to all spheres of the analysis strategies. So most of the conventional searches at the LHC assume that the new BSM particles decay promptly. But is it really necessary to assume this? And the answer is no. Because even within the standard model, there are long-lived particles. So what happens if our new physics particles does not decay promptly but have longer lifetime? So we must open the door to the lifetime frontier. A particle is said to be long-lived if it has macroscopic decay length c tau to be greater than equal to few millimeter. Usually prompt particle will decay at this IP. However, a long-lived particle will traverse some distance before decaying to the standard model particles. Sorry? No, this is the proper decay length. Now I will, in the lab frame, it will come with the beta gamma factor. Yes, of course. Yes, I will come. So as Ranjan said, so how to detect these LLPs? So to detect the LLP, there are three key ingredients. First is how it is produced. Like, is it produced in a meson decay or in a Higgs decay? Because depending upon the production, it can go either in the forward direction or in the transverse direction. And the second key factor is the boost factor that basically includes the kinematics. Second key factor to detect the LLP is its proper decay length, and also what is the decay products, that is the standard model products that it's decaying to. And finally, where to place the detector. That is basically the distance traversed by the particle, that is the beta gamma c tau. Now I will discuss a little bit about the ongoing and also the proposed LLP searches. So the key difficulty to detect the LLP is we are unaware about its mass and also its lifetime. And this basically makes it impossible from the first principle to make a single detector that can cover all the range for all masses and c taus. And you can see for these four collaboration, there are at least one proposal for dedicated detectors to detect the LLPs. So the left hand side plot is basically the reach and coverage of LLP experiments in mass and C-tau planes. For LHC, it's more sensitive for heavier LLPs greater than 10 GeV, and it covers all the C-taus. However, forward detectors like phasor chip NA62, those are specifically designed to detect LLPs for lower masses and also low to medium C-taus. While the transverse detectors like Codex B, Mathusal, Alex, these are sensitive for low to medium mass range and higher C-taus. The right hand side plot is for in the LLP mass versus root-S energy. For the forward detectors, this is more sensitive for root-S less than few GeV, whereas the LHC and the transverse detectors are proposed for this higher root-S energy. Yes, which one you are asking, this plot? No, it can. So the main detector has all. It's I think 25 meter for FCC-ee, and for the running one, it has also this. Sorry, FCC-ee. Sorry, the main detector volume. Yes, and for CMS, there is proposal for this facet that will be at 101 meter, the dedicated detector in the z-axis, and also there is Mathusla. So, no, what you are asking probably I am missing. It tens of meter for this LHCS and for its neon spectrometer. Yes. It's not mass dependent. Okay, so this was the snow mass report for 2022. The y-axis is where to place the detector, the distance from the IP, and with the mass range. So after that also there are many proposals that are not included here, and I will discuss few of them in detail. So coming to the forward detector, the forward search experiment phasor, it is already running. It's 480 meter, the LS is 480 meter from the Atlas IP. It's a cylindrical detector with radius 10 centimeter and 1.5 meter length, and it's collecting data for 150 femtoburning per integrated luminosity. Initially there was proposal to upgrade it to phasor 2 with a higher dimension of radius 1 meter and length 5 meter, and it was originally proposed to take 3 autoburn inverse luminosity data in 2026 to 2035. However, recently people are talking about forward physics facility FPF, And they are talking to place the detector more away from Atlas at 620 meter, and by increasing the length of the detector, they have shown that the similar sort of sensitivity can be reached as phasor 2 was designed for, and it's expected to take data from 2029. From CMS side, they are, yeah. Yeah, but with increasing the length, they can get the same sensitivity. They have shown. But there is no space to, yes. Yes, all low mass. Yes, yes. So from the CMS side, there is proposal for forward aperture CMS extension. This is basically extension in the CMS detector placed at Z equal to 101 meter. It's a cylindrical detector with length 18 meter and radius 50 centimeter, and it will be sensitive for LLP masses greater than 1 GeV and sensitive for C taus in the range 0.1 to 100. No, they have said in the proposal it's greater than 1 GeV. No, it will come from like meson decay or Higgs decay or something like that. Yes, but if you LLP mass, yeah. So I don't know why it's greater than 1 GeV sensitive. I need to look. Yes, but that's what the forward detectors are meant for, to look for. Yes, that will be higher for the light particle. Yes, but that and C tau in the range is 0.1 to 100 meter. For the beta gamma times C tau may be within the range, because C tau is less, right? Yes. No, but you can see the C tau is up to only 100 meter. They are saying it will be sensitive for the proper decay length. So I think the beta gamma C tau must be within the dimension of the detector. It's within the 80 meter starting from 101 to 119. But I'm not very sure why it's 1 G greater than 1 G. Now from the LHC-B side also there is a proposal for monopole and exotic detectors at LHC map model. It's already running. It's in the forward region of LHC-B at 50 meter from the IP. And there are 4 parts of the detector, each 10 cross 10 array of 100 scintillator, each of size 10 centimeter, 10 centimeter and 75 centimeter. And the projected luminosity for this is 300 femtobarn inverse. Coming to the, sorry? This is already running, map model. Codex P is, okay. So for the transverse detector, there is proposal for Mathusla. The original proposal was for a box sort of detector with dimension 25 meter, 100 meter and 100 meter. It's a surface detector above CMS interaction point, projected for 14 TeV HLLHC. And it was supposed to take data for 3 autobahn inverse and for sensitive for masses greater than 10 GeV and C tau greater than 100 meter. Then there is also transverse detector from LHC-B side 20 meters away from the interaction point with dimension of 10 cross 10 cross 10 box detector, and if possible 20 cross 20 cross 20, and this will be taking data if approved for 300 femtobarn inverse, and will be sensitive for theta greater than 1 meter. From Alice side also there is proposal for I don't know the technical terms. They are saying they will use the L3 magnet and the TPC as the detector, and this is 12 meter long detector with inner radius 0.85 meter and outer radius 5 meter, and they have shown that if approved, even with 100 femtobarn inverse luminosity, they can have comparable sensitivity as Mathusla or exceed for some models. Now for Atlas, there is Anubis. It's 20 meter away from IP, and it will cover this mass range. Yes. Yeah, but it's in shaft. Okay. 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 Yeah, I was also shocked, but I cross-checked the number. It was 10 to the power 6. Yes. I will again check this reference, but yeah. हाँ Toshma, you did Anubis. Okay, yeah, no, I also don't know. I also was shocked by this 10 to the power 6 meter, but I didn't follow it much. Okay, now for the fixed target experiment, there is SHIP. It has been recently approved in 2024, and it will start taking data from 2026, and 2 into 10 to the power 20 proton target collisions are foreseen in 5 years of operation, and this is sensitive for masses less than 10 G. There are 5 years. At least in, okay, I will check. I saw it in the recent European strategy report. Okay, okay, I will check. So there are also proposals from NA62, NA64 and many more. However, till now there isn't any proposal for 100 TeV FCC-ee, and Biplav and other people, we together proposed 2 detectors, one in the transverse plane D-light and one in the forward direction 400. So compared to the 14 TeV at 100 TeV, we are not constrained by any space, and it's a high time that we should look into this opportunity very seriously and optimize the geometry and position of this detector. So D-light is detector for long-lived particles at high energy physics of 100 TeV. Depending upon the size and cost and everything, we have proposed 3 configurations. D-light A is same size as the Mathusla. delight B is 4 times the dimension of Mathusla and delight C is 2 times the dimension of Mathusla. And because of the larger size, delight B gives the best sensitivity to detect the LLP. Similarly, we proposed a detector forehand forward experiment for 100 TeV. It's a phasor 2-like detector but with different dimension and the position is different. And we optimized for different radius and length, and we see that forehand C, that is a cylindrical detector of 5 meter and 50 meter length and placed at 50 meter from the IP of FCC-ee, it performs the best. Now to compare the sensitivity of the dedicated detectors, we assume a dark scalar model. So here we have extended the standard model sector minimally with a real scalar phi, and the last term basically introduces the mixing. And after electroweak symmetry breaking, the neutral component of the Higgs and Higgs doublet and the phi will get wave. And changing from the gauge basis to the mass basis, we will get the physical scalars. So H125 is our SM-like Higgs and phi is known as the dark scalar. Now this phi can talk to the standard model particles via its mixing through the SM-like Higgs, and if the mixing is very less, you can see phi to FF bar decay width is proportional to the theta square, and for small theta this tau is large, which is inversely proportional to the C tau. Sorry, tau is small, which is inversely proportional to the C tau, making C tau large, and thus phi can become the LLP. So this is the lifetime times theta square in mass plane, and in today's talk I will be assuming phi to be very light, mass range varying from 100 MeV to few GeV, and I will solely discuss the phi coming from the B2K phi decay, and for small mixing angle the branching is given by this equation, which we will need later. Now this is the sensitivity for dark Higgs model. The magenta color line is the phasor 2 projected sensitivity, the yellowish line is for sheep, the light blue is for codex B, the green is for Mathusla, the deep blue line is for our proposed detector forehand C, and the red line is for delight B. And you can see going from 14 TeV to 100 TeV, in terms of mixing angle we can enhance the sensitivity by orders of magnitude. For 1 GeV it's like 15, and for for 0.1 GeV it's like 15, and for 1 GeV it's like 20. Delight even performs better in this dark Higgs model. Now so far I discussed about the yes, because B-mesons are produced more in and also for the more B mode phi, and also it's more in the forward direction. Because of the dimension, and also no, for delight we couldn't draw the line because it's a box detector, and we because of the computation this thing we need to generate at least 10 to the power 10 events or more than that, which we couldn't do. And anyways the upper parts are will already be discovered by other experiments. Sorry, you were asking something? So now I will discuss about how the FCC-ee can give us any additional probe to detect the LLPs. And since we are entering a high precision era, probably the next collider would be the lepton collider. And FCC is supposed to operate in 4 center of mass energies. the Z pole at 91.2 GeV, W plus W minus threshold at 161 GeV, AZ production at 240 GeV, and TT bar threshold 350 or 365 GeV. And this is the luminosity reach over years, and the Z pole is expected to get 150 autoburn inverse after running for 4 years. Okay, I will again take you to the plot that I showed 2-3 slides back, and I will now motivate you the benchmark choice. Z to BB bar, I will discuss. So, as I discussed, that many of the dedicated detectors that are proposed, we don't know whether they will be realized in future or approved. So, in this scenario, we would like to see if FCC-ee can give us any additional proof. For example, if SHIP is approved, the BPA1, BPA2 and BPA5 can be probed at SHIP. Similarly, BPA4 and BPA6 will be covered for the projected HLHC-B analysis. Similarly, if phasor 2 is approved, this green line, BPA2 and BPA4 can be probed. Yes, but the sensitivity will be the same. They have shown that. No, same. It's far and bigger. Similarly, if SHIP and Mathusla both are approved, yeah, BPA1 can be probed. But for benchmarks where like BPA3, which is at the boundary of phasor 2, SHIP and Mathusla, even if we see few signal events, still we would be needing a main collider detector which can probe the signals further. And also we want to see if there is any benchmark points that is not approved, not covered by any of the projected or ongoing experiments like BPA7. So this is the choice of our benchmarks. So this is basically summarized in this table, and you can also see that depending upon the mass, the dominant decay modes change. Sorry, can you repeat? For giving the? Yes. This is their projection, yes, this, yes. Mathusla. I think one thing is will be the luminosity of 3 autoburn inverse, and for this projection is 300 femtoburn inverse. Or no, there should be other factors also. Yes, that's the small region. They have just scaled analysis. Yeah. No, they They do.
But more restrictive to the backup
Tracker.
that below and they use that part. Not here background is also high. I don't know the answer actually because yeah. So we try to
We
find
are
out some
firstly
we can look into it actually.
yeah, we are also first trying to see how this LHCb luminosity is the projection limit is changing, but we found that they have simply factorized it with the luminosity, and we are not sure whether this is correct. Better. Yeah, so the choice of benchmarks are also, you can see that the dominant decay modes also changes as a function of mass. For example, for a 0.4 GeV, the main decay modes are pi pi and mu mu, whereas for 1 GeV, it's dipion and dication. For 2 GeV, 3.5 GeV, it's pion, kaon, and also muon. And for this BPS 7 4.4 GeV, the dominant decay modes are CC bar and tau tau. So now I will discuss the analysis, benchmark specific analysis for these 7 chosen benchmark points. But before going to that, let me briefly talk about the analysis strategy. So the number of events that will be detected within this main detector of the FCC-ee, that is the idea detector, innovative. For what of B?
X of B, that's a standard part. X, B or X.
XS, okay.
That's a standard part. So you all try to simultaneously correct that.
Maybe
the timing, right? Suppose this happens, right? So suppose the B decay, so you get the X of S, and then after some time you get the
K, yes.
You use the timing, they will know that it's definitely coming from this decay. Yes. No, I'm also doing the timing. The question I'm asking is because technically you are detecting 5, so you don't know where it is coming from. Maybe
Yes.
statistically it's coming from B. No, whether it's coming from B or not. Suppose I do this couple, right? Suppose 5 goes to tau plus 1. So I know it's 5 goes to tau. But where is the 5 coming from? Technically we don't know. Unless we detect the other one, then we will nail it out.
No, I don't have that slide, but yeah. But in the paper it's there. We talked about that. Yes.
But I think constraints doesn't
Backgrounds are still used.
I want to say that, I mean, just
dear sir, please.
Because of some background like
Okay, so the number of events that is detected within this idea detector is basically the sigma BB bar, that is the at Z pole, that is 9.05 nanobarn, and the luminosity reach is 150 autobarn inverse, the branching of B to this X5, and the detector acceptance A, that is basically taking into account how much of the signal events generated is decaying within the detector, and also the signal efficiency, that also takes into account the detector efficiency component. And the factor 2 here is taking the fact that 2 Bs are produced and those 2 can decay to the LLPs. This is for FCC-ee. Mm-hmm. In the FCC, this is basically 10 to the power 12 terazi this region. Okay. Okay. Yes. Okay. Okay. Maybe one should look.
he gets into cost of something. He has done some basic calculations.
No, no, we were. No, it's just E plus E minus Z to BB bar.
Meenakshi is asking what would be the like exclusion limit from LHC base. I think yeah, it will cover.
It will cover,
He
yes.
has done some kind of basic calculation. I think it's very strong.
Okay, should I proceed? So this is the schematic diagram for idea detector. So it will be placed at one of the IPs, and idea detector is basically around the beam pipe, and this is basically the 1/4 part of the detector. So the innermost layer is the vertex detector, the black dots. So this is made up of silicon pixels, and it has very good tracking and identification for charged particles. Then there is this drift chamber DCH, which also has very good tracking efficiency, high momentum resolution, and particle identification. After that, there is a 2 Tesla magnet, and then there is a small region, this greenish color. This is the pre-shower. This is basically in the barrel region as well as the forward region of the end cap, and this can identify photons and charged particles, and it can also identify pi zeros from its decay to 2 photons. After that, there is this dual readout calorimeter DRC, which can basically identify from the energy deposition of electron, photons, or hadrons, and it can also distinguish between these. And finally, the muon spectrometer. So the dimensions are given in this table for each detector component. And assuming 100% efficiency, first we show how much number of events are contained in each part of the detectors for our chosen 7 benchmark point. And we can see for BP-A2, BP-A3, BP-A4 and BP-A6, most of the events are contained within the main idea detector. However, for BP-A1 and BP-A5, due to their high CTOs, most of the events are going outside the idea detector. Okay, so this table is assuming 100% efficiency, but in reality it won't be like that. And we have used some of the papers and so have seen some of the fixed efficiencies, that is the energy threshold that is needed to turn on these detector components, and we couldn't find any efficiency in a fast detector simulation like DELFIS, so we have used these efficiencies for our analysis. And yeah, so now comes the standard model backgrounds. It can come from the mesons as well as the baryons. Some of them has low CTOs, but due to higher production cross section and the exponential nature of the CTO, it will go further away, and some of them can also be produced from another long-lived particle, and we have to take into account everything. So for generating the background, we have used Pythia 8, we have used the Z production cross section at 91.2 GeV and then Z2 QQ bar, and have hadronized everything. And this is the 3 categories that we have divided our standard model backgrounds. So first one, you can see the Jeffshai background. The DT is basically the transverse length of the LLP from the IP, and it can go up to 50 meter. For D plus minus, millimeter, sorry. Yes. And for D plus minus, it can go up to 100 millimeter. And the third category is for this case, it can go up to 1 meter or so. So we have done a fitting over DT and have seen DT greater than 150 millimeter can kill these first two kind of backgrounds, but it's impossible to kill the third category, and we will discuss this as analysis wise. So the what's no, it's the proper CTOW of the for KL, KS, all those. In standard model, the long-lived particles. Yes. And like I would like to mention here that for these background generations, we have generated 10 to the power 9 events, but Terazi is 10 to the power 12, and we couldn't do that much of event simulation, so that's why we have done this fitting for these backgrounds. So this is the schematic diagram for the signal, and as well as the standard model backgrounds that can mimic this signal. So we have finally used some important variables that has helped us to reduce the or kill the background. So first one is the location of the vertex, D vertex, that is whether we are doing the analysis in the vertex detector or muon spectrometer or DCH. Then the number of charged particles created at that vertex, NCH, total energy of the particles, E, the dt, and also the number of muons, pions or kaons originating at the vertex. Also the invariant mass of the final state particles associated with the vertex, M vertex, and the impact parameter of the vertex, D0. We tried many functions, but I don't know, Camellia, did you use like this? No, first we check like it's ax square plus bx plus c, then ax cube plus bx plus c, something like that, and then yeah, then polynomial fitting basically. Yes, we have first generated the events, then calculated mean wise what are the number of events, and then extrapolated it. Yes, that's what I think we have also taken into account. Yes, that can fake as background. You are saying, right? That can also be a source of background. That's what you are saying. Okay, so we are taking this B2K5. That's why we have taken this Z to BB bar. Yes. No, but this is a this is not C tau, this is ET. This is DT, the transverse direction, the position of the LLP. It's not C tau. So finally I will discuss about the final state specific analysis. So for BPA1, BPA2, BPA4 and BPA6 we had significant amount of phi going to mu mu, and you can see I am just showing the final plots here. So the brighter line basically is the standard model background for Jepchai, and no, we are not vetoing, we are just putting cut on DT to get rid of the background. That we can't. Yes. We are just showing what is the mass at the vertex. Yeah, but you can see with this two demanding 2 muon energy greater than 1 GeV, and we are doing the analysis in the vertex plus DCH. It's not that long. Then it will. So finally we have given this sort of curves to kill the background, and this is the number of events diamond analysis up to the muon spectrometer, and the red bracketed events were assuming 100% efficiency, and you can see like taking into account all the detector efficiency and things like that, the number of events are almost half of that. So for BPA4 and BPA6 we are getting moderate number of events. However, for BPA1 and BPA5 the situation is not very good. Then the dipion and dication final state, there we found another difficulty because proton was faking as background coming from lambda 0 to p plus pi minus. And you can see at 1.1 GeV there is a large TT, and also for Ks to pi pi there is another bright spot. And we then think to divide the analysis in two parts. When the mass of the phi is greater than equal to 1.5 GeV, it's fine, we can do the vertex and DCH analysis. But for the other benchmark points, we went to the muon spectrometer to do the analysis, and using this sort of curves, finally for this for masses greater than 1.5 GeV, we could do the vertex plus DCH analysis, and for all the benchmark points, we have given the muon spectrometer analysis. Finally, coming to our BPA7, that was 65% decaying to tau tau. So there another variable came to rescue us. So sorry, CC bar, sorry, CC bar and tau tau. Dominant was CC bar, yes, sorry. So we demanded 3 charged particles, M vertex greater than 5 GeV. E vertex greater than 5 GeV and M vertex greater than 1.5 GeV, and finally with this sort of curves for BP7 we could get this number of events. Okay, now I will again take you to this 100% efficiency events table, and as I mentioned, for this BPA1 and BPA5 most of the events were going outside. And even within this vertex DCH analysis or muon spectrometer analysis, we could get only ballpark of 5 events. So here we need some dedicated detectors to analyze for these benchmarks with higher C-taus. So at FCC-ee there is already some proposal for HICAT. This is a detector designed for FCC-ee and CEPC, and it's a 4 pi detector placed with the cavern oil, and they have shown the sensitivity for heavy neutral lepton, and compared to the main detector they have shown that using this HICAT the sensitivity reach can be probed at least half of the magnitude. Then there is far detectors for these are similar detector like Mathusla, and they have also done for heavy neutral lepton and Higgs 255 detect. And finally there is this laycast layered cavern surface tracker. This is a cuboid sort of detector of 40 meter, 30 meter, 20 meter, and they have also shown efficiency for this Higgs 255 neutralino and HNL. However, we couldn't find any dedicated detector for decaying LLPs coming from B-meson. So to design a detector, we first need to understand the directionality of the LLPs. So we plot here the theta of the LLP with the beam axis, that is the z axis. And we see that for 0 to pi, every region is populated with peak at pi by 4 and 3 pi by 4. So any central detector covering eta from 0.5 to 2.5 will be a good choice to detect this LLP. So credit goes to Camellia. She has done 60 different configurations, and finally we came up with 3. So first one is IDEA like detector, and it's full cylinder with inner radius 6 meter and outer radius 11 meter and total length of 20 meters. The second one is the half cylinder with the same dimension but placed 45 degree to XY plane. And finally the G2 is our D-light B-light detector. And with this we see that for this BPA1 and BPA5 we could get good number of events because of the higher dimension. G2 will perform the best, then A1 and then B4. Okay, so this is the comparison between vertex DCH, the inner component of the IDEA detector versus the outside detectors, and we can see for C-taus greater than 1 meter the dedicated detectors will perform better. And this is the signal efficiency as a function of mass and C-tau for these 3 dedicated detectors, and I'll skip that. Yes. No, even for this higher, it will be. Yes. Yes. Okay, so this brings me to the conclusion. So in this work, we have used the excellent particle identification for FCC-ee, and we have quoted the expected number of signal events for FCC-ee after the analysis cuts for each benchmark for their dominant decay modes. Finally, we have also extensively studied possible dedicated LLP detectors and have found that A1, B4 and G2, these three sort of detectors perform the best among the dedicated detectors. In this paper, we have also done the detailed analysis for Higgs 255, which I didn't present here. If you are interested, you can go and check. So that's all. Thank you. Tau we haven't done because it was very difficult to do. Yeah, I can.